Hello everybody, welcome to the session for Enterprise Code Race 222 titled Achieving Linear Scaling of Multi-Threaded Algorithms with Core Count. This session applies or is demonstrated on the product from our company called ULab Studio for Delphi, of which we have also a variant for .NET and .NET Core, and of course it is dealing with the efficient multithreading. What linear scaling means and why it matters. 10 times more CPU cores will ideally shorten algorithm execution time by 10 times. Intel Alder Lake features 24 hardware threads, Intel Raptor Lake has 32, CPUs are on a steep core count upper slope, and generational improvements of execution on a single core have been very modest over the past 12 years. So the only way that is open to scale our performance is mostly in the direction of increasing the multi-threading capacity. These problems are still unsolved also for C++, Python, .NET Core, not only for Delphi. So it's important to emphasize these are industry-wide problems which are deeply rooted in the different aspects of the software development process. Symmetric multithreading has been around for about 15 years in the mainstream market for consumers. So Intel Core Duo processor line was introduced in 2006. CPUs with 4 CPU cores are still mainstream for today, but the effect of inefficient software on the server market is staggering. The ever-increasing core count per CPU is not going away, so it makes sense that we have a look at this and see if we can do something about it. When new CPUs are released, they also come with benchmarks which demonstrate how this CPU is faster than the previous versions or the competition. These special algorithms which test multi-thread performance can scale linearly with core count. They show theoretical peak performance if the algorithm is done right. And now we will examine the constraints on what it means to be done right and what effort and what methods are needed in order to achieve this goal. Now this recipe that we are looking here is actually a short summary of what we'll be all looking at, and it is a preview of different things that we will analyze. The first requirement is to launch the same number of threads as their virtual cores. The second requirement is that most of the time all CPU cores need to work with their own private and dedicated memory. This can be only level 2 cache or level 1 cache. This requirement is actually quite obvious because as the CPU core count increases, we need to reduce any kind of interdependency where one core has to wait on the other or share some resource with other cores. And one of the main problems that we need to solve is how to completely eliminate or reduce as much as possible the sharing of the memory of every individual CPU core. Finally, if we access the main memory and level 3 cache, this should be done relatively infrequently, or ideally, let's say 1% of the algorithm execution time. It's important to understand that level 1 cache is about 100 times faster than main memory. So this means that if you can write your algorithm right, it will really run 100 times faster on one core than it runs if it is not running from the level 1 cache, but it is running from the main memory. This may seem like a science fiction, but it's possible. It can be done. A single variable assignment located in main memory takes the same amount of time as computing average of an array with 100 elements located in level 1 cache. So if we create a situation in our algorithm where we need to write or read something from the main memory, this is comparatively hugely expensive, and this type of memory access is very difficult to analyze and to detect why something is taking this long. So what we will examine in the first part, this is what we have planned for today, is the an analysis of the CPU cache, or how to write code so that we get to have our data into level 1 or level 2 cache. And the second part deals with the critical sections. In the second part, which are just planned for tomorrow, we look at atomic operations and at thread count, the number of threads which we launch for our algorithm, and what happens depending on the number of threads. So if we move right to the first problem, this is the CPU cache. The memory hierarchy on CPUs is on this picture, and we see that every core has its own dedicated L1, which is 32 kilobytes approximately, can be also 64, and has a really large memory bandwidth for this memory, which can be 2 terabytes or more per second. Comparatively, level 2 cache is going to reach 700 gigabytes per second. Level 3 is going to reach 200 gigabytes per second for all available cores together, which is shared among all cores. But if we access main memory, we get roughly 20 gigabytes per second, and per memory channel. So this now also depends on how many memory channels are populated in our hardware, and if we are using server which has more memory channels, the significance of memory channels is that each thread gets to use at most only one memory channel. So one thread cannot work across multiple memory channels, and to take advantage of all the memory channels we have to launch at least as many threads as there are memory channels, and this is not yet a guarantee that we will also get to use all the memory channels. It's up to the memory controller and the kernel to decide what will get to be assigned to our process and to our application. To my knowledge, there is no way to explicitly control the number of channels which will get to be used by a single process. We will return to these schematics many times in the near future, just to demonstrate what is where we are on this hierarchy. So the objectives. What are the objectives when we write the code? The first is to optimize our algorithm so that it works mostly with level 1 or level 2 cache. How is this done? If our data has to fit into this size. So if we go back, our data may not exceed 32 kilobytes, or it may not exceed 2 megabytes, or it may not exceed I don't know, 16 megabytes during its lifetime. If the algorithm does not fit into the level 1, level 2 or even level 3 cache, the best scaling factor will be proportional to the number of memory channels, but not CPU cores. So here at the bottom we have memory channels. We get 20 gigabytes per, let's say because there are also generational differences, but if we say that this is roughly the order of magnitude, the 20 gigabytes per second, and maybe we have 4 memory channels for a server CPU, and there are maybe 2 CPUs in the server, so we get together 8 channels. 8 times 2 is 160 gigabytes, but for this we need to launch at least 8 threads and need to split them between both CPUs so that one gets 4 and the other one gets 4. So here we see each thread always gets to use at most 1 memory channel, and all memory channels in the system need at least 1 DIMM module in their slot or they are off. So DDR5 has some extra features. If I was reading correctly, 1 DDR5 channel can serve 2 threads, but I still have to get a machine to try this out, to what extent is this possible. So how to get your data into the CPU cache? Need to read the data more than once, and the size of the data, which is repeatedly read, must be smaller than the cache size of the desired cache level, and the higher level caches are progressively smaller and faster. The cost of loading data into cache. First read of the array is at the speed of the main memory. Second read of the same memory location is already cached. To cancel out the cost of loading the data into the cache, need to reread the same data at least 10 to 100 times, because the loading from the main memory is so slow. If the algorithm is such that it only reads input data once, such algorithm cannot be threaded much on the CPU, because all the data resides in the main memory, and the main memory is as fast as it is. Now, if we remember what Apple did with its M1 CPU, it has vastly increased the speed of the main memory, so that it nearly reaches, or that it has reached, the speed of level 3 cache on Intel CPUs. This does solve one aspect or one problem for a specific class of algorithms, but still it does not provide the possibility for linear scaling with thread count. Okay, so now if we have data which is less than 60 kilobytes, for example, in level 1 cache, but the speed does not increase, why? The highest level cache bandwidth can only be maxed out with vectorized instructions which load multiple consecutive elements of the same array in one cycle. If we only put the data into the cache, but we don't also use instructions which really push on the bandwidth, then nothing happens. Need library, compiler or write assembler that uses those instructions. And Intel AVX 512 is about 20 times faster than non-vectorized code. Otherwise, the generated code is simply too slow, and it does not matter if our data lands in level 1 or L2, because memory bandwidth is not the reason why the the performance is lacking. So the final result will be that it doesn't matter if the data lands in level 1, level 2 or level 3, which in level 3 definitely it will get to be there, but we will not be able to see the effect that we have more memory bandwidth available, because we are not using instructions which actually take advantage of that extra bandwidth. So Intel went into great lengths to provide enough bandwidth so that you can load in one cycle, let's say 4 elements of the array, compute the same operation on all 4 elements, and then store the result of this array back into the memory. Here we have a very simple example how to max out level 1 cache bandwidth. So we are just increasing 1000 elements by number 1. If we use a vectorized library, that would be an expression like this. This operation can be vectorized. It can be done with the AVX instruction set, and we can continue. Within the high bandwidth vectorized code section for loop, in order for this all to work, what we just discussed, strictly consecutive array element access is required. This means that consecutive is one index higher than what it was before. We have no if clauses which work on per element basis of the array, so there is absolutely no branching. There are no function calls that work on each element of the array element separately. So all functions called must be in the vectorized form. Even advanced C++ compilers can vectorize only simplistic branching. Here we have one example. So Intel C++ is, and I'm sure other compilers also will be able to vectorize this operation, even though we have some branching here. But as soon as you make these expressions more complex, the possibility for vectorization is lost. When the vectorization is lost, we cannot take advantage of the extra bandwidth provided by the level 2 and level 1 cache, and well, we miss out on the possibility to speed up our algorithm by additional 20 times. The first 5 times can be achieved simply by making our data reside in level 3 cache. Now there is one note here, so to say, that the threading library can have a thread index parameter, and this thread index parameter can run from 0 to thread count, where the thread count is the number of threads launched by the threading library, and this allows the thread to access always the same cached memory in the level 1, level 2 CPU cache of the same CPU core on which the thread is running. If you can imagine that so if you consider that the myThread event is going to get to be called more than once, and that we are not always sure which thread is calling this event, the thread index is providing us with the information which thread it is, or on which core it is running, at least for some time, because the CPU is also moving the threads from one core to the other, but not to the extent that this would completely invalidate or make the level 1 or level 2 CPU cache meaningless, because if it would be meaningless, then it wouldn't serve any purpose. But this parameter allows us to know on which core we are, and when we know on which core we are, we can also have some variable that is associated with that core or with that CPU cache. If we don't have this parameter, then we don't know where to store this data, and we break the caching rule. This is this sums up the theory, and now we will be looking at some of the examples, that we have about how this looks on actual algorithms, what this means for real world applications. So here we have one demo from our product, which is going to vectorize code as a function of vector length. So when we vary the length of the vector or the length of the array, which is being processed where all the elements are processed in parallel, but not yet threaded. So this has to do with execution on one core, but it is using vectorized instructions, and we are varying the length of the vector and trying to see how fast is the execution going to be as a function of vector length. And this vector length has the function to get our data either into cache level 1, cache level 2, or cache level 3. So if we run this, we have here 4 lines. One line is the plain function as when written by Delphi. We can see that the performance of the speed of the processing of the elements does not change with the length of the array. The reason why it doesn't change with the length of the array is that the processing does not take advantage of code vectorization, because the instructions are so always working on a single element, and because the code is so slow, it never gets to be bottlenecked by the memory subsystem. Then if we look at the next line, which is the green line, this one uses vectorized code, and we see here that there is some overhead for very short array lengths, because we need some encapsulation logic in order to wrap the arrays into one block, into one vector, and need also a way to manage the memory, how we allocate and how we free the memory for these vectors. If we examine, for example, the ratio between the green and the red, we have here 2.6 milliseconds, and here we get down to 0.15. That is around 15 times faster is the vectorized code. So what we are doing is that we are computing a math function called Maxwell PDF, and we are computing this function for every element in the array. And here we have 128 elements in the array, here we have 16,384 elements in the array, and we are doing the same operations on all the elements. But of course every element can have different value. Then if we look at the next line, this is the yellow line, we have here something called block vectorization, and the block vectorization is going to break up our vector into smaller pieces so that we never exceed the size of the level 1 cache, even when we have a vector which is much longer than the size of the level 1 cache. And the effect of such processing is seen here at the end, when our code starts to exceed the size of a level 1 cache. Then the yellow line becomes more performant than the green line. And finally, we have here a line which is called vectorized expression. The vectorized expression is a syntactic sugar which allows us to write the code in a more readable and fancy way. So we are now looking at the source code of this benchmark, and you can see that if you compute the function for every what we are computing here, so we take one source and we put it into destination and computing the same function for every element, and this is without the block processing. So we are using vectors. So res is a vector, and doing the vectorized way. And if we look at the expression, then we are still using vectors, like TMP is a vector, but we can write the mathematical expression as if though we are working on a single value. The advantage or the disadvantage of this approach is that every time we make some expression of two vectors, we get to have a temporary variable, and the creation of this temporary variable possibly results in memory allocation, and this is generally not a good thing. But in case of Delphi, it is possible that this extra memory allocation is done in a safe way, so that this does not defeat the CPU caching policy. Yes, and then we run all the 4 examples and draw the charts. And to have vectorized code, to have vectorized instructions, what lies behind this? You have, in general, there are 3 options. You write something in one of the compilers which is able to vectorize the code. This will be one of the C++ compilers, and then you call those functions as primitives from the Delphi, as in calling into a DLL. Another option is to use pre-optimized libraries like those provided by Intel, or by those Intel has, for example, one API, or those provided by Apple, because Apple has the accelerator pack, and those functions are internally vectorized. So we, for example, here our product is a library which is calling those vectorized primitives depending on the vendor of each hardware of each CPU, to provide the highest possible execution performance when working with arrays. Here we have another benchmark where we are looking at the speed of evaluating different functions in comparison to what a scalar evaluation takes and what a vectorized function can perform. For example, these functions here are are from Intel IPP library, which is part of one API, Intel One API pack. If we run the benchmark, you can see, for example, that the speed of the scalar version is 1.8, and the speed of the vectorized version is approximately 6 times less for the sine function. And similar story repeats for other functions also. One specialty are complex functions, because the more complex the mathematical expression which can be vectorized, the bigger will be the gain. And here, for example, for the complex number sine function, we have around 20 milliseconds, and for the vectorized function we have 1.25, and that is roughly 15 times faster, not only 6 times faster. Of course, this all is only possible if we can keep our data into level 1 CPU cache. So our block of data on which we are working has to be less than CPU cache level 1. These are CPU cache level 1 results. We have 1000 elements in the array. 1000 times 8 bytes is 8 kilobytes, so the cache is maybe 16 or 32 kilobytes big, and we have enough storage for source and destination. If our data is not fitting into the CPU cache level 1 or perhaps not even level 2, if our vector is much longer than this, then of course the benefit of code vectorization will diminish, because the memory bandwidth of the memory subsystem is simply not able to feed the CPU at sufficient speed. We have still not entered into the problem area. Now, as we increase the size of the vector, we have also disproportionately increased the time it takes to compute the result. So it's not that now when our vector is 10 times longer, it will take 10 times more time, but it will take 20 or 30 or 40 or 50 times more time for a 10 times longer vector. And this can then be observed from these results. So what we can see on these results is that the advantage of the complex number of functions has diminished, but the advantage of the real number functions is still remaining strong. This indicates that the memory bandwidth for these functions is not yet a problem, because they perform so much math on one value that by the time they need the next value, they already have that next value available, and they don't need to wait for it. But you can see that if we went from advantage of 15 to 1, here we have now maybe for the sine function for a complex number we go from 660 to 280. That is a little more than 2 times. So this code advantage, the performance advantage, is now only roughly 2 in compared to what it was before when it was 16. Now we come to the code example, which is dealing with the memory channels and the cache. So if we run let's say one copy operation, read and write across multiple threads, we can see that we start with some level, we add one more thread, we get double performance, but to get to 4 threads we only increase our throughput marginally, and we cannot do anything much more if we go to 8 cores. So this looks like a dual channel memory system. We can also see the approximate performance of the memory subsystem, which peaks out at 20 gigabytes. Now if we go to CPU cache level 1, here you can see a much more steady climb as a function of the core count, and this is the linear scaling with core count that we are after. It's not completely linear, because the CPU is also going to power throttle its own frequency. We all know that the CPUs today has several levels of turbo mode, when it will increase its own frequency if the performance load is short enough, and then it will slowly reduce its frequency on one or more cores as the heat dissipation increases, to remain within its own power envelope and the capacity of the cooling system. Here is another interesting test, where we are testing the subsystem of our library, which is returning vectors and matrices, which are pre-allocated and which have their own memory pools. So this means that when individual threads will ask for a new variable, they will get this variable without having to wait, or without being in danger to have a collision with other threads. So such a memory manager you could call superconductive or fully parallel. So when we are allocating this one new variable, we are guaranteed to never enter a critical section and never need to use atomic operations. So if we run this test, here we see the performance or the time the threads need when running on a single thread, and here we see what happens when we run on the multi-threaded, and here we have an example of the times the cost or how long it takes inside of the thread to obtain to create a new object. And with the superconductive approach, the time reduces considerably, but for the get memory it remains the same. Why are these orange and red and green much more? Because they actually do a lot more. They allocate bigger objects, allocate more variables, and so on. So they will shrink, and the code will scale with thread count. Here we have another example of the effect of the vector length on the both on the threading and on the speed of processing on a single thread. So when we had here block processing, this worked only on one thread, but now we have the same algorithm or a similar algorithm working on multiple threads. So we will do this block processing in parallel and see what happens. The blue line shows the advantage of the superconductive memory manager in compared to the classic memory manager when executing vectorized code. So one thing which is immediately very obvious is that we only need to handle memory requests which are up to roughly 2000 elements or 16 kilobytes in size. Anything which is bigger, for 8 cores, which is what we have on this computer, it is already good enough if we handle only vectors which are shorter than 60, memory blocks which are shorter than 16 kilobytes, because for longer vectors, the effect of having a fully parallel memory manager diminishes very quickly. So why? Because the cost of processing the data in bigger memory becomes disproportionately bigger in compared to the cost of allocating the memory. I hope it was possible to understand this, but of course every memory allocation has a certain fixed cost, which is typically not so much dependent on the size of that memory. So if we allocate 16 bytes or we allocate 16,000 bytes, the cost of calling the get memory function might actually be very similar, or if not exactly the same. Of course, under the assumption that the memory manager is not zeroing out this memory or doing some other stuff with that, like moving it around or resizing and reallocating. And this fixed amount of cost, when we call the get memory function, this is most visible and most sensitive when we have very short arrays. And we can see here that if we use the superconductive memory manager, our vectors can be 1000 element long, which means that they will fit into level 1 cache. So if they fit into level 1 cache, then we get that extra performance, which is maybe 20 times more than level 3 cache, or maybe only 5 times more than level 2 cache, but still we want to have vectors as short as possible so that we can get into the higher level of the CPU cache to get better performance. So why do we want to have vectors short? If we assume that level 1 cache has 32 kilobytes and that one array would have 200 elements and 8 bytes per element, which gives 1.6 kilobytes, that would allow us to store 20 vectors or 20 arrays which are 1.6 kilobytes long into the level 1 cache of one core. When we are writing expressions that deal with multiple variables, we actually do need more than one variable many times. We have maybe variable A, then variable B, variable C, and to compute that what we want to compute, we need more vectors, and to be able to have more vectors, they need to be short enough to fit into the limited space of the level 1 cache. Here we have another benchmark which is not so directly related to cache, but it does build upon that, and is quite important when it comes to performance. So let's suppose that we already store objects which are created rather than always creating the objects from startup. In this case we see 32 arrays with pre-allocated 1024 elements, and this we are comparing to allocating the same 32 arrays with 1024 elements but not having any cache. So you can see that by using this system we save, we are about 10 times faster to allocate memory and to initialize objects and all that stuff. Here we come to one final benchmark for CPU cache, and this has to do with efficient multithreading. We will spend a little bit more time on this. This was a problem that was being solved by one of our customers, so we have included it into our demo project. And I will now press the start, and it may take some time, maybe sometimes few minutes, but we can skip forward in time. Okay, so the benchmark has finished and we can see that for the pure Pascal code it takes 35 seconds. We can have a look what is in this case pure Pascal code. This is the FCPU and this is the function which is being computed. These arrays are complex, and this function is also complex function, and also this function, this what is here inside, I believe is no, these are real functions, but the result is then complex. So if we just use vectorization using one CPU core without multithreading, we can achieve a speed of 3 by roughly 10 times. Now if we make use of block vectorization, which means that we try to fit our working block size into level 1 cache, we get a further improvement on one core, still no threading here, but to 2.47. Then if we refine our this block processing, we get down to 1.76. What means this refinement? Let's have a look at this 2.47, what this looks like. Here we have vector declared, and we are processing this instead of within using two loops. Now we have only one outer loop, and all these expressions are vector expressions. Now if we go into the block processing, we can still have vector expressions, but if we break this down and do it with less temporary variables which occur due to results of the expressions, when two vectors multiply they get a temporary variable, and then the temporary variable is passed on to the calling function. Here we don't have any temporary variables, everything is specified explicitly. We also see here one structure from one system from the library how we can break down one long array into smaller pieces. We call block init on each of the arrays that we want to process in smaller pieces. Then we call while not block end, and at the end of this while clause we have block next, block next, block next for each of the blocks. And what this does is just moves, let's say if you have 10,000 elements in the array, first when you call block init you have 0 to 1000, when you call block next you have 1000 to 2000, the next time you call block next you have the next 1000 element long block for all three. So you are really processing the array in smaller pieces in order to remain in the level 1 cache. Yes, and the key advantage of writing this out rather than just having it comfortable is to remove the creation of temporary variables, but at the same time we can see that we get to be pretty darn fast even if we are using temporary variables. So it's not like that we have completely lost it. And so yes, now we start with the threading. First we try to multi-thread the code naively. We just go I believe we go directly at this one, not is it vectorized or not vectorized, I don't recall, but the point is the result is not very impressive. Now yes, of course we try to do it with big vectors. We try to do it with big vectors which are not blocked. So what happens is that we max out the bandwidth of the level 3 cache. Because the level 3 cache bandwidth is maxed out, we cannot achieve performance improvement. We cannot achieve performance improvements over running the same algorithm with only one thread. In fact, it just only gets to be slower. It's not faster. If we get to have blocks which are we process the array in blocks so that our working set of variables fits into level 1 cache, then the sky opens up and we can achieve further improvement, because now each core is working with its own distinct private memory in level 1 or in level 2. And now we actually can achieve scaling with core count and roughly additional tenfold or 5 to 10-fold improvement over what we had before. And this is not the end yet. We can try to use anonymous functions. The anonymous functions are not much slower, but there is some penalty with that. Then we can do threaded and do handwritten blocks. This, instead of taking this function, we take this function, and we achieve the performance which is even higher than that. 26. We can try to use the yes, all this is done with mtx vecthread library, not with t-parallel. But if we would use t-parallel, the speed is somewhat less. This is explained then later in the other part of this presentation, what the problem is here. and the key problem is that we launch too many threads, and that we need to limit the number of threads that T-parallel will launch, and then we also get much higher throughput. As a final example, we also have the same algorithm written in OpenCL. The OpenCL can be simplistic, which means that we try to use vectors in a similar way as we use for the CPU. This is not as effective, of course, but it does give you a very quick start, and it offloads your CPU, and it doesn't take a lot of work. So let's say it's quick result, but it's not a big effect. If we write custom kernel for the OpenCL, this specific algorithm has the possibility to execute on GPU at amazing speed, which is not many times possible, but it is possible for this one. And you can see that it is 100 times 35 is 3500 times faster than using only one core, or if we compare to the optimized version of on the CPU, it is still 26 times faster. Now we are getting slowly into the areas of the speed ups which are interesting, because mostly people think, yes, but why would we optimize something? It would only be 2-3 times faster, and so on. It will never get to be 100 times or 1000 times. But yes, of course, it can be. It can also be that you can make something that your algorithm can be executed at speeds which were before for you completely unimaginable. So next time we are going to have a look at the critical sections, at atomic operations, and the maximum thread count. What is the influence of the number of threads that we launch, and of the threading library. I would like to thank you everybody for the attention. I hope this presentation was useful for you, and I hope to see you for the second part. And of course, the software that we were using, this is available on internet. If you go to www.uresearch.com, you have the option to download the trial versions of our products and also of the MTexist library. In those trial versions, you can see the source code of everything that we have been looking at today. You can examine this into detail, try to find some faults, some problems that we missed. Of course, I would be happy to hear everything that you might wonder or have doubt or questions about. And of course, on the GitHub at uresearch, we have these demos, source code available, so that you can share the links to the individual source files and directly examine the source code without actually the need to install some large libraries into your computer and system, or being afraid to compromise something. Or although I can say that we have been doing this for a very long time, and you should be safe if you want to try and see something. So thank you very much to everybody. Thank you for your attention, and hope to see you for the second part of this series. Bye.
Okay, so let's see if Jens, if you have your webcam, you can turn it on. If not, you can just use your microphone and talk. Well, I don't see your camera, but I should be able to hear you now.
Can you hear me?
Yes, I do.
Yes, sorry about the camera. My hairdo today is not the best, so I apologize for that.
That's fine. I understand. All right, so thank you so much for that session. There was a conversation going on in the organizer chat. I love these sort of sessions, and I can see the amount of effort that's gone into your libraries and into the session, and it's fantastic. But it's one of those things I need to watch it like 2 or 3 times to get all this stuff out of here.
You see, it took many years to make these examples. The library has been on the market for 25 years now, and every year or every 2 years we came up with one example to point out one specific point. So if you cannot digest this in 1 hour, it's not surprising, but it is a pointer to you what to explore and what the options are, what the possibilities are. So
Right.
in my thinking, there is a lot of possibility which is not being used.
It makes sense. It makes sense. I just put a link in for the order on the website if you want to go out and buy a copy, or you got trials available for download as well. And you pointed at the GitHub too. This is it's interesting with these sorts of things because there are a lot of people out there that their programs are just perfectly fast the way they are. But there are a number of people that are like running into scenarios where it's like, oh, I really need to eke out that extra performance, and so it's great that this option's out there for them, that people that do need to get the maximum performance possible, which
Well, I
is
think the most important conclusion would be that if you want to have something running 100 times faster, it is possible. This would be my
exactly,
message for today.
yeah. Something I always tell people is they're like, is it possible to do? And I'm like, it doesn't matter what you're about to ask. The
Yes.
answer is always yes. You can get there eventually. It just might take some effort, or it might take some libraries or whatever the case would be. And then so this is a great example of that. Like you said, if you're like, I want it to be 100 times faster, okay, let's do that. So
Yes, that's right.
fantastic. All right. Well, thank you so much. And we'll be joining you tomorrow for your session, the next session on part 2.